In this section, we are going to look at some applications of double integrals. I'm not going to cover every topic that the book has, just the topics of center of mass and probability. So the first thing that we're going to look at are what the book refers to as lamina, which are basically just thin plates. And I'll probably just refer to them as plates. What we're essentially doing is we're taking some region in the plane, you can think of some little blob that we'll call D, and we're going to imagine that this thing has a little bit of a three-dimensional thickness. So kind of imagine that it's just has some thickness to it. And we want to ask ourselves what kind of physical properties such a plate might actually have. Now, we could actually just assume that this thing is kind of constant and uniform, where it has the same density throughout. But if we're going to do that, we actually don't even need to use double integrals. The book actually talks about these, I think, back in chapter 8, where it actually just uses just integrals of one variable to find the center of mass or of a plate with constant density. Here, instead, we want to kind of consider our density as varying over the plate. So let's recall what density actually is. Density is mass per area. So in a little area, what is the mass of that area? If we're talking about a density that varies, we're going to call this rho of xy. So at the point xy, we'll say that it has some density rho. Rho here is the Greek letter for r. Not entirely sure why they picked rho for this instead of something like delta. But the idea is that at a point xy, we're going to take some little region around it. Probably a square or rectangle. Honestly, it doesn't really matter, because we're not really going to be finding the density this way. Most of our problems, the density will be given to us. But we do want to have an idea of what we're talking about by this density function. But the idea here is that this little piece of our disk has some area, which we'll call delta A, and it has some mass, which we'll call delta M. And we want to see what is that limit as that area goes down to 0. I mean, the mass should be going down to 0 as well at the same time. And so, in some sense, this is treating the density as the derivative of mass with respect to area, in some weird sense. It's not really a derivative, but it kind of looks like one. And that really does actually play a role in how we're going to turn this around and actually use it to find various things for the disk, for the plate later on. In fact, the first thing we're going to do is use this to get a formula for what the mass of the plate should be in terms of the density function. If if density is the derivative of mass, you might think mass should be the integral of density. In fact, that's exactly what we see. You can make this all formal if you like, the way the book does it, by essentially dividing up the plate into a grid of areas, and then using the fact that the mass of each of those things should be approximately equal to the density of a sample point times the area of the piece, and then add all those up, get a Riemann sum, and in the limit you just get the double integral of the density. So mass is in fact just the double integral of the density function over the entire plate. But honestly, that's not too mind-blowing. We're just basically taking the density that's defined in terms of mass and then changing it back into mass. So what have we really accomplished here? Well, this actually gets very useful if we want to talk about what the center of mass is. but we're going to have to actually build up to that. We want to derive some formula for what would be the balance point for our plate. If, say, we have our plate here, can we find some point in here that if I essentially put the plate on a spike at that point, the plate shouldn't fall over? I mean, obviously, it would be tipsy in a real world situation, but mathematically, there should be some point on the plate where we can balance that entire plate. And we want to identify what that point would be. But before we even do that, let's consider a much simpler case of finite many points on a line. So here we have a line where we have a bunch of points. We're going to go ahead and actually give it a 0 so we can actually refer to where these points are on the line. We're going to say this is at x1, x2, and so on. So we have in my picture we have 5 different points that are at these different x values, but each point has a mass attached to it. There we go. So 5-point masses on a line. We're going to ask ourselves, is there a point, let's say x bar, that balances all 5 of these points? Or maybe all n of the points if we want to be more general than that. So we have our xi and mi for 1 through n different points in the more general case. This x bar we'll refer to as our fulcrum point. Because you can kind of think of this as being a kind of like a lever or a seesaw or something like that. And we want to know, is there some point where we can actually balance everything out so that if this was some physical situation, it wouldn't tip one way or the other? Well, what would cause it to tip would be a torque. And torque around some fulcrum point is given by the distance that the actual force is applied to the bar times the force is actually being applied. And this force is measured actually perpendicular to the bar. We're not going to get into a more technical description of what torque is. We want to use vectors there and the cross product and stuff like that, but that's not really what our goal is right now. When we're talking about our center of mass, all of the forces are actually these downward gravitational forces, and we want to keep the bar horizontal. So we essentially going to be replacing the forces here with just the force of gravity at each of these points. So the torque at a given one of these given xi mi's, they frequently use the Greek letter tau. The distance, what we're going to do there is take xi, or actually let's put the x bar first. X bar minus xi. We don't know what x bar is. Hopefully we'll be able to solve for it essentially. And I'm putting x bar minus xi. That's going to be positive in this picture for x1 and x2, but it'll be negative for x3, x4, and x5. Essentially what that's going to do for us is kind of have the ones over here be essentially the positive torques will be the ones where they'll move this in a counterclockwise direction, whereas the negative ones will be in a clockwise direction. We want those to balance each other out. So having negatives here actually helps us out. And then the force, like I said, it's going to be the force of gravity. The force of gravity on a mass of, say, mi is just mi times acceleration due to gravity. And then we want to look at what do we get if we add all these up. If we add all these up, so they just have a sum of all of these, this is over I from 1 to n. And if x bar is the center of mass, this sum should be 0, because that means the total torque is 0. If it is anything other than 0, the bar is going to move based off of that torque. So we want it to come out to be 0. Can we somehow use the fact that this comes out to be 0 to solve for x bar? That seems like maybe it'd be a kind of a tall order, but it actually turns out to be possible. So let's look at this thing and see if we can solve it. Well, first things first, everything here has a factor of g. We can just divide that out. That's actually not important overall. We can also split this thing up. So we can distribute the mi to each of these two terms, and then a sum of differences is just a difference of sums. Basically, we're looking at a whole bunch of terms here. We can reorder them however we want to. We can add them up in different ways. So this really becomes the sum of x bars times mi's minus the sum of xi's times mi. And we'll go ahead and move up to here for the next line. This thing here, we can go ahead and pull out the x bar. We're just factoring out x bar. And then we're going to go ahead and move this over to the other side. And then we can go ahead and divide by this sum. And I'm going to leave off the I equals 1 to n, just to make it a little less cluttered. So we have a formula here for the center of mass of these points. And what you can note here is that the sum of mi, that's just the total sum of all the masses that we're talking about. This thing that we have on top, the sum of the distances, all these xi's times mi's, this is what's going to be called the moment of the system. The moment of the system is the sum of xi, mi. And we're going to be finding these moments for these more general cases. But first of all, we need to actually put this in a two-dimensional concept. So we're only working here with points on a line. Let's actually talk about points in a plane. So we have our plane here. We have various points. Say we have those points there. Those points will have coordinates of xi, yi, and they'll have masses of mi. What can we actually do here to actually find out what would be the center of mass? So if we have all these points, is there some, say, x bar, y bar, that balances all of these points? Kind of the balance. So if these were all kind of on just a flat plate, and then you put all these masses on it, is there some balance point? Well, it turns out what we can do is just look at the x and y coordinates separately. Essentially, we can find the moment of the system around the x-axis. That'd be what we can denote as m sub x. That's going to be the sum of the xi mi's, just like we had before. And then we have a moment around the y-axis. it's going to be m sub y, which is the sum of the yi's, mi's. And then the center of mass is what we get by just dividing mx and my by the total mass. So we say this is x bar, y bar is equal to just mx divided by m. So just the sum of all the m's. And then ym divided by m. Okay, so that's what it is when we have point masses. When we have just a finite collection of points where all the mass is concentrated at those points. What happens if we're in our more general situation where we have just this density where we can't really talk about the mass at a particular point? The mass at one particular point is 0, but in a little section of it, we have an actual mass. Well, we're essentially going to take these things and we're going to turn them into double integrals. We already know how to find the mass. We already found a formula for finding the mass. What we're going to do is turn these sums into double integrals. So if maybe we've taken a little sub-rectangle from our, maybe we'll call this Rij. So we kind of broken up our region into rectangles, into a bunch of little rectangles. We've denoted them by Ij because we're making a grid of them like we've done in the previous sections. On this we have some sample point. Maybe we'll call that sample point Xij, Yj, Ij. It has some area. Call that delta A, Ij. And it has some mass, which we'll call delta M, Ij. Well, the density, remember the density at this point, is the limit of a ratio of these things, so it's approximately equal to delta Mij divided by delta Aij. And so delta Mij is approximately the density at that sample point times the delta A for the change in area. If we use these delta Mij's in place of the Mi's that we have in here, and then for xi and yi, we use the xij and the yij, then we can say that the moment sub x is approximately, if we kind of imagine each of these rectangles as playing the role of a point mass for the entire region, we approximately have the sum over all the i's and j's. I'm not even going to say it's from 1 to n or anything like that. We're summing over all the i's and all the j's times the xij times the delta mij. That's our formula from before. We take the x's times the m's, and then we add them all up. Well, that's just what we're doing here. But now we're replacing the delta mij's with this more complicated formula. I guess I should still make this an approximation. So xij, rho of xij, yij, times delta aij. So, doing a lot of approximating here, but everything does work out when we actually take the limit. As we take the limit, as these rectangles or whatever regions that we're looking at, as they go down to 0, then this actually gives us a formula. So the moment around the x-axis is the limit of these Riemann sums, And I guess they put stars in here that I didn't put in here. Whatever. And I'm just realizing that I kind of messed up my association here. So the moment around the x-axis is actually referring to if you consider the y values, because we're really thinking of if we map these all down all to the y-axis and then thought about it as if we're working with this line as being the y-axis and thinking about how that would tip. So actually, I should be switching these. So this one here is around the y-axis, and this one's around the x-axis. So this is around the y-axis, and this is the x-axis. That actually does switch these. And this where I sometimes get confused here is just the fact that the formula for, say, x bar is the yes, I need to swap these as well. So the moment around the y-axis is still my, but it involves the x's. The moment around the x-axis is still mx, but it involves the y's. When we find the center of mass, we do put my sub m for x bar. So finding x bar does take the formula that involves the x's divided by the mass. And then y bar takes the formula involving the y's divided by the mass. It's mostly a notational thing. I kind of get myself confused about it sometimes. What that's going to do here is change this x to a y. We're looking for the moment around the x-axis, and that's the one that involves the y's. And so our formula for m sub x is the double integral of y times the density over our region. The similar formula for the moment around the y-axis, we have the double integral of x times the density, gives us our moment around the y-axis. And then we use these formulas in order to actually, we basically take these moments and we divide them by the mass that we already know how to do, and we get our center of mass. So x bar, the first coordinate of our center of mass, is 1 over the mass that we find by doing the double integral over the density. So here, down here, m equals the double integral of the density. And we multiply 1 over m by the double integral of x times the density. And then we do the same thing for y bar. So you just have to remember that m sub y and m sub x are kind of swapped from what you might expect them to be. And I get myself tripped over that too. Let's actually work out some examples. So here we're given a triangular region, D. So this is the triangular region with vertices 0, 0, 2, 1, and 0, 3. If we're, let's go ahead and draw that out. So 0, 0 is the origin. We have 2, 1. So let's say around here, maybe. Actually, I don't want to go too high there because I need to be able to go up 3. Then we have 0, 3. Let's say it's up here. We have this region D. We have a density function. The density is x plus y, so it starts out with a density basically 0 down here. But as we go out, the density is increasing. We want to find out we want the mass, we want the center of mass, and that will involve finding the moments as well. So we'll start with the mass. The mass is equal to the double integral over our region of our density function x plus y. Of course, here we do need to identify how we can integrate over this region. If we look at the graph of this, If we were to try to view this as a type 2 region, we would have a problem because we have a different rightmost function for this top part versus the bottom part. So, but as a type 1 region, this actually is not too bad. The top is this line here, which you can actually go ahead and find is the line y equals 3 minus x, and the bottom curve is this line here, which is the line y equals x over 2. I'll leave it to you to actually figure out those lines yourself. Of course, the x values are going to go from 0 over here to 2 over here. So we're going to be looking at the integral from 0 to 2, then the integral from x over 2 to 3 minus x. Our function is still x plus y, and we do dy and then dx. The integral of x plus y with respect to y is not too bad. X just becomes xy. Y becomes 1/2 y squared. Now we get to plug in our limits. So we have x times 3 minus x plus half of 3 minus x squared. But then we subtract what we get when we plug in x over 2. So x times x over 2 is half of x squared. Then half of x over 2 squared is going to be a 1/8 x squared. Remember, that's subtracted. It was added here, but now we're subtracting it because of I'm distributing the minus sign. Before we actually do the integration, you'll want to go ahead and combine like terms. I'm going to leave out the steps of doing that. I'll leave that to you to actually do for yourself. It's just some algebra. But it turns out what we have in here all simplifies down to 9/2 minus 9/8 x squared. If we integrate that, 9/2 becomes 9/2 x. 9/8 x squared becomes a 3/8 x cubed. I had to divide by 3, so I took that from the 9. When we plug in 0, we don't get anything. When we plug in 2, well, the first part becomes a 9. Second part, we have a 3, but then the 8 actually cancels out with 2 cubed, so we have minus 3. And so ultimately, we get 6. The mass of this triangle is 6. The area is definitely not 6, but the mass of it is 6. Actually, what would be the area? The area, because we could use this base here, is 3. This height, if we go just perpendicular to this base, is 2. And so the area of it would be 3 times 2 divided by 2, or just 3. So this has an area of 3, but it has a mass of 6. If we want to look at the moment, or at the two moments, we're going to have to find both of them. Let's start with m sub y. Remember that the moment around the y-axis is going to be, we take x times our density function of x plus y over that region. But we don't have to set the region up again. So one advantage of all this process here is once we know how to set it up one time, we know how to set it up every time. Because we're describing that region the exact same way, we're just changing the function that we're integrating. So unless putting an x in there causes something to not be easy to do in one way versus the other way, we're just going to set it up the same way every time. So we're still going to set this up from 0 to 2, from x over 2 to 3 minus x. This time our integrand is, well, let's distribute that. So x squared plus xy dy dx. We do the integration the same way. The function's different this time, though. we're integrating this with respect to y, so this becomes an x squared y plus half of xy squared. In fact, since we're integrating with respect to y first, none of this actually changes for this first step, aside from the fact there's an extra factor of x. So actually, all the work that we did here will just have an extra factor of x for this in this thing here. So ultimately, this is going to change into the integral of 9/2 x minus 9/8 x cubed. And again, I'm going to leave that to you to actually work out for yourself. Now the extra factor of x comes into play because it's going to change how we integrate. So this is going to be turned into a 9/4 x squared. This is going to become a 9/32 x to the 4th from 0 to 2. When we plug in, well, again, when we plug in 0, it's not going to, nothing's going to remain there. But when we plug in 2, we have 9/4, but then times 4. So we get 9 there. Here we get 9/32, but then times 16. That's 2 to the 4th power. So we end up with a 9/2. And 9 minus 9/2 is 9/2. So that's our moment around the y-axis. Apparently this is going to take up a lot of room. Our moment around the x-axis, we do pretty much the same way. We're still integrating over d. This time we're going to be multiplying by y instead of x. We set it up exactly the same way because there's not really any reason to change in this case. But we're going to be integrating this time xy plus y squared. And this time, the fact that we are integrating with respect to y, it will change our results for the first integration, so we don't really get to copy a lot of our work like we did last time. Integrate this with respect to y, we have 1/2 xy squared plus 1/3 y cubed from x/2 to 3 minus x. We go ahead and put our limits in, so we have a 1/2 x times 3 minus x squared plus a 1/3 3 minus x cubed minus, when we plug in x/2, we do have to square that, so we have a 1/8 x cubed, and then we have over here, we have the 1/3 and a 1/8, so we have a 1/24 x cubed again. Again, I'm going to leave it to you to do all the algebra of simplifying this thing, but actually, in this case, the simplification gives us a very nice result. In fact, all the quadratic and cubic terms cancel out. This whole thing, this whole integrand, simplifies to 9 minus 9/2x. Which is really nice, but the work to get to that point was not so nice. But oh well. We go ahead and integrate it. The integral of 9 is 9x. Integral of 9/2 x is 9/4 x squared. We're taking that from 0 to 2. Of course, 0 again doesn't give us anything. When we plug in 2, we get 18 minus, well, the 4 and the 2 squared cancel out, so we get a 9. And so we get 9. That's our moment around the x-axis. And so our center of mass, x bar, y bar, well, we're going to take m sub x and m sub y, and we're going to divide them by m. So x bar is going to be 9/2 divided by 6. Y bar is going to be 9 divided by 6. And we simplify that, we get 3/4, 3/2. That's our center of mass. And it's going to be actually a point that's further up here, closer to this edge, because the density is much lower at this point over here than it is over on along this edge. So as the density gets more as you go further out, that means our center of mass is further out, and it's not going to be what you might say is the center of the triangle. Let's do another problem. So in this case, we have another lamina or plate that's occupying the part of the disk x squared plus y squared is less than or equal to 1 in the first quadrant. So we're basically taking our unit circle and only looking at the part in the first quadrant and the stuff that's inside the circle in that quadrant. We want to find the center of mass of this thing, but its density is not uniform. Its density at any point is proportional to the distance from the x-axis. So they didn't actually give us the density function, but it's easy enough to figure out. So the distance from the x-axis is actually y, and so there's going to be some constant times y that's going to give us our density. Ultimately, the constant here won't matter, but we'll keep it here in order to show where it actually kind of disappears. So we'll have a c in all of our calculations. But the point here is that the density depends on how far away we are from the x-axis. Of course, we'll start with the mass. We'll look at the double integral over this region. We'll call it d. I guess I didn't name it, so we'll call it d. Of our density function, c times y, dA. Of course, we can integrate this however we want to. Since we are dealing with a quarter circle, that might be a sign that polar coordinates may be useful, as long as the integrand itself doesn't get too messy. But remember, y is just going to be r times cosine of theta. Or, sorry, y is r sine theta. X is r cosine theta. So we want to talk about this thing in polar coordinates. Well, in polar coordinates, we're really just looking at r theta, where r is going to be anything from 0 to 1, and theta is going to be anything starting from 0 and getting to pi over 2. So this is 0 to pi over 2 times 0 to 1, or not times, but the integral from 0 to pi over 2, then the integral from 0 to 1 of our c times r, or c times y, which is r sine theta. Don't forget that we do have an r dr d theta. And whenever you use polar coordinates, don't forget that extra r. One nice thing here is that since we do have just numbers here, we don't have any functions of r in terms of theta. We can actually pull this apart. I'm actually going to pull out the c, in fact. Pull that c out. It's just a constant. We don't need it inside. We'll pull out anything that has to do with the theta and put it in the integral d theta. So we have the integral from 0 to pi over 2 of sine of theta d theta. Then we have the integral, we have two r's, so we're integrating r squared from 0 to 1. The integral of sine with respect to theta is going to be negative cosine. The integral of r squared is going to be 1/3 r cubed. Go ahead and plug in our values. Cosine of pi over 2 is 0. Cosine of 0 is 1. So we're going to be subtracting a negative 1. So this part just becomes a 1. This part, when we plug in 1, we get 1/3. Then we subtract 0. So the mass is c over 3. So whatever our constant of proportionality for our density function divided by 3 is the mass of this quarter circle. If we look at the moment with respect to the y-axis, remember this is the double integral over d of of x times our density function of cy. We're going to set it up exactly the same way. So we go from 0 to pi over 2, 0 to 1. We have x and y this time. We saw the c in there. X is going to be our cosine theta. Y is going to be our sine theta. We still have an extra r, dr d theta. We can pull everything apart just like we did in the last one. I'm going to pull out the c. I'm going to take all the stuff that is involved with the theta and put it into its own integral. So you have sine theta, cosine theta, d theta. Then we have the integral for r's. We have 1, 2, 3 r's, r cubed. And now we have to think about how we are going to do these integrals. Well, with the sine times cosine, the way I approach this is I made a substitution. I set u equal to sine. That means that du is cosine theta d theta. And so I'm basically going to be integrating u. Well, the integral of u is 1/2 u squared, but my u was originally sine. So we have 1/2 sine squared. Kind of rushing through a few steps here, but these are things that you should know how to do already. And I'm going to make that look like a 2 and not a 3. 2. Integral of r cubed is 1/4 r to the 4th. We go ahead and plug in our values. So we have 1/2 of sine squared, but at pi over 2, sine squared is 1. So we have a 1/2. At 0, we have a 0, so that just turns into a 1/2. When we plug in 1, we get a 1/4 minus 0. And so our moment around the y-axis is c divided by 8. Finally, we'll look at the moment around the x-axis. Remember, this is the integral, the double integral of y times our density function. But we're going to set this up exactly the same way. This time we saw the c, but now y squared is r sine theta squared. We have the extra r, dr d theta. We can pull out the c again. When we pull out the stuff that has thetas in it, we have a sine squared. And then we have r cubed. We have two r's here because we have to distribute the square. Then we have an extra r there. In fact, we already know what the integral of the r's are because we just did that right here. When we integrated r cubed from 0 to 1, we got a 1/4. So actually, we can go ahead and replace that in the next step with 1/4. So we have c over 4, but we need to know how we're going to integrate sine squared. So if you remember, we have a formula for that. Sine squared, we're going to use what we call the power reduction formula. Sine squared turns into a 1/2 minus 1/2 cosine of 2 theta. So remember, sine squared turns into this. Cosine squared turns into 1/2 plus 1/2 cosine of 2 theta. And now we can actually do the integration. So this becomes a 1/2 theta. Then this becomes a minus 1/4 sine of 2 theta. From 0 to pi over 2. When we plug in 0 into the sine, we get 0. When we plug in pi over 2, well, the sine actually sees pi. Sine of pi is also 0. So both of these are going to give this part equal to 0. So actually, again, the 1/2 theta is going to be the most significant part. When we plug in pi over 2, we get pi over 4. When we plug in 0, we obviously get 0. So this is going to be c over 4 times pi over 4, or c times pi divided by 16. Now we get to divide those. So remember, we're taking the c over 8 and dividing it by c over 3 to get x bar. And then we're going to take this c pi over 16 and divide it by c over 3 to get y bar. And here's why the c doesn't matter. Everything was multiplied by c in the first place. The c's are all going to cancel each other out. This first one becomes 8/3. Not 8/3. The 8's are on the bottom, but the 3 down here is going to be on top. So the other way around. 3/8. And then again over here, this 3 that's on the bottom is going to be on the top. That pi is going to stay on the top, and 16 is going to be at the bottom. So we'll have a 3 pi over 16. And that is the center of mass for this quarter disk when we use this density function. Alright, so I'm going to leave this video here. This is all about center of mass. The book does go a little bit further than this and talks about what's called the moment of inertia. That gets into essentially the role that mass plays in linear motion. Inertia. I don't really want to get into it here. Yeah. Mass plays a role in inertia for linear momentum. Moment of inertia here is talking about essentially a rotational version of that. Sort of how we had to deal with torque in actually deriving our formulas for center of mass. If you're interested, you can take a look at that. I'm not going to get into it here, but I am going to cover another topic in the next video. So I'll see you there.